So an electric field, as I love how Crash Course explains it. They say a measurable effect generated by any charged object. So it's measurable and it's an effect that one charged particle has on another. So I like to think of it as a region around a charged particle in which another one would feel a force. And this is dependent on a number of things, but if you think about it, simply put, it's what's going to happen to one charged particle when placed near another. And understanding the equations for electric field will help us understand this and wrap our heads around it. So there's two equations. The first equation for electric field is Coulomb's constant multiplied by our charge over r squared. So Coulomb's constant, you can see the value here, times we've got the charge. So if we're trying to find the electric field for this positively charged object, it would be the charge of this positively charged object and then the radius. So that distance right there if we're finding the electric field at this point. So this helps us understand that as we get farther away from an electric field, there will be less of a force, less strong electric field. Then the second equation simplifies that for us. And this simplifies it for us because if you plug in Coulomb's force here to this force right here, one of the charges cancels out and you actually get this equation right here. So this makes it a little more easy to understand. An electric field is equal to force over the charge of a positive test charge. Okay? And you can think about that as the positive test charge is the one placed inside the field that you're trying to figure out. It's also important to understand and note that this electric field has direction, and it's in the same direction as the force. Okay? So we're actually going to have a review question to see if you understood everything that was going on, and I hope you did. So if you just pause the video, read through the question, and see if you get the answer. Perfect. So which of the following would not increase the electric field strength? We've got A, increase Coulomb's constant, which, as you might have assumed, is impossible. We were not going to increase a constant. That's why it's constant. B, increase the distance of the test charge from Q. So if we increase distance, what's that going to do? Well, the electric field strength is going to go down. So that would definitely not increase the electric field strength. And then increase the charge of Q would increase the electric field strength. So B was the correct answer. Now that we understand a little bit better electric fields, we're going to go into electric field lines. And these field lines are a visualization of how a charged particle will react when placed in a field. They help us understand how multiple multiple electric fields interact and things like that. There's a few rules we have to follow in drawing these field lines. And number one is that the lines go outward from a positive test charge and go into a negative test charge. Number two, number of field lines leaving or entering is equivalent to magnitude of the field. And we'll see that on the next slide, but basically means the more lines going into or coming out of your charged object, the stronger the electric field. And then number three, the field lines can never cross. And why is that the case? Well, that would mean that at one point, so let's say at this point, if they were crossing, that the electric field in one place would be acting in opposite directions, which is impossible. So the field lines will never cross. So here's a better visualization of the second rule. The more lines, the greater the field strength. So you see here, this would have a greater electric field, this negatively charged particle, as opposed to this one that has less lines going into it. And you see the positive the field lines go out from the positive into the negative. And then we're going to see as well later on how two charged particles would their electric field lines would be drawn and how those electric fields would interact. Briefly, just wanted to mention that conductors don't have an electric field inside of them. That's because all the charge goes to the outside. The charge can freely move throughout a conductor, so there's no electric field inside. This can be a great application. These electric field lines and electric field can help us with parallel plates, capacitors, an application that's in television and other devices that we use, because it helps us understand that there's a uniform electric field inside. It's not going to curve, but it's uniform. And then we got our second review question. Will an electron placed in an electric field go in the same direction as the field lines? So pause the video and try this one out for yourself. Okay, so an electron is a negatively charged particle. If we placed an electron here, would it follow these field lines? Would it be attracted to this other negatively charged particle? And as you may assume, the negative repulses the negative. So it would actually want to be attracted to this positive test charge. And that would not be following the field lines that we've drawn, because if you remember, they go outward from the positive and into the negative. We're going to talk about how these two interact. So we know it's not yes, and then the two no's, no, because charges will go in whichever direction the arrows indicate. That's not correct. Answer is B. Good job. So multiple charges, how are they going to interact? Well, they're not going to cross, so we're going to need to remember our rules. And they go outward from the positive into the negative, so we're still going to follow those. So if they're two particles of the same charge, it's going to act like this. They're just going to go out, they're never going to cross, these will go on forever. There's actually no electric field right there. And then the same thing happens for the negatively charged particles, except for the field lines go into them. Then you can see down here kind of small, goes outward from the positive and straight into the negative, just like you saw in that last review question. In understanding these electric fields and electric field lines will help us to solve some mathematical problems that I'd like to go over. We've got 3 examples we're going to go over real quick. And just a few tips. Remember your units. The charge needs to be in coulomb, and the radius needs to be in meters. A lot of times it's given to you in centimeters, and then the charge in microcoulombs, nanocoulombs, whatever it may be. Let's go to the first example. It's the simplest one that we have today. And remember this equation that we gave you on the second slide. Here are your units. If you're a little bit confused and you like to write it out in units. So we've got a 2 microcoulomb charge, -1 microcoulomb charge. You see the distance is here from this star. So what's the electric field at this location? Well, I like to start by drawing my field lines. I know that field lines go into the negative charge, so I know that's the effect that it would have here. And then they go outward from a positively charged particle. I'm going to plug in the charge into our equation to see what the electric field will be for each of these particles. So I plug it in, I make sure it's in coulombs, not microcoulombs, by timesing it by 10 to the -6th. Remember, it's squared, the distance squared. Okay, so I've got both my components, and I've put down here the equation. I like to visualize it. I put this in absolute value because if you think about it, they're working in opposite directions. This positive charge pushing, this negative charge pulling. So if I subtract the negative, then I will actually be creating a greater electric force, or electric field, excuse me. So what I'm going to do, I am going to subtract this absolute value from this electric field value, as you can see here, and that's what would be felt there. So number 2, we're getting a little bit more complicated here. We've got 2 charges, and they're working in different directions with 40 microcoulomb, 30 microcoulomb. So I draw my field lines. They go outward from the positive charge. Okay, we've drawn that. I plug the values in to find the electric field for each component, and I'm actually going to be drawing triangles here. So I know at the location that I'm trying to find the electric field at, we've got 30 microcoulomb working upward in the upward direction and the 40 to the right. Well, if you look at that, that's a triangle right there. So if I move this 30 microcoulomb over here, it just helps in visualization. I've got a hypotenuse. That's actually going to be my answer right there. So I have the components for each side of my triangle. I use the Pythagorean theorem and I solve for the hypotenuse. That is going to be the electric field at that location. And just keep in mind, how would you solve this if it was negatively charged? Well, because you know how to draw your field lines, you just have a different looking triangle, but it could work the same way as two positively charged particles. So for our last example, it's a little bit more difficult. We've got three charges all working on this, and it's in a square shape. We've got our field lines drawn just to understand what they're going to be doing to this point, this location space. If something's placed there, I'm going to plug those in. Okay. And remember, I forgot to mention this. We're assuming that this is a positive test charge placed here. If not, then it would be different how our field lines would react, correct? Because it's a positive test charge, that's why these are pushing, and this would be pulling on this positively charged object we're going to place inside the electric fields. And if you look here, we did the same thing as before. We solved for the electric field. Each component, remember for this radius, you're going to use Pythagorean theorem for this charged particle, and I've put that here. You can screenshot this and zoom in if you need to. And we're going to do the same thing as last time. We're going to draw the effects of this positive charge into a graph looking sort of thing. So we've got the -5 nanocoulomb pulling down. You've got the 10 nanocoulomb there. Well, but you've got this one diagonal. You're going to have to break that down into x and y components, okay? Remember direction, which way is positive, which way is negative. And I like making a little chart here. And you'll total up your values. You can see 0 here because this -5 nanocoulomb, it doesn't have an x component, just a y. You'll total this up, and you'll have another set of values for x and y. And if you have another x and y component, well, great, you can make another triangle, okay? And you make another triangle, and you'll do the same thing as you did on the last problem. You use the Pythagorean theorem, find the hypotenuse, and that will be the total. Electric field. This can also help you understand which way the positively charged test particle would react, and things like that. So hopefully that wasn't too quick, but due to time, I can't go too in depth. You can pause it here though. And then I've zoomed in on this component to help you understand a little bit better. So we know this 10 nanocoulombs working in that direction. The -5 is going to be pulling it downward, and that other one pushing it up. And I'll break it into these x and y components, add the x and y, and then make another triangle. Just wanted to say thank you for your time. Hopefully this helped you understand a little bit better electric fields and field lines, and also be able to complete homework problems and things like that might arise. Thank you so much for your time.